like probably because of midterm. I remember like last time it was there were more people here, and a few of the grad students they actually have something like special this week. I'm not sure, but that's probably the reason why they didn't came. But doesn't matter. Just we'll get started. Okay, so yeah, welcome everyone. So I remember last week we were talking about what were we talking about? Yeah, we were talking about binary search, right? Okay, binary search tree. That's what we talked about last week. All right. So before starting the materials, there's a quick announcement that I actually find another great site. I know I talk about this a lot, but this one is actually pretty good. So you can see here is another one. So different from the previous one we have, which is this one, like a comprehensive list. This one talks like specifically targeted to CP. And normally, let's say just that you want to search for, let's say segment tree, which is a topic that we probably won't cover a lot today. And let's say you have like a bunch of these results. And the first one is a binary search tree. Okay, sorry, the first one is advanced segment tree. So you can find here that there's actually a lot of materials here. And so segment tree is one of those few topics in CP that you don't actually have to go very deep about it because it's actually very hard and very academic. And a lot of time you just need to know like half of this like article in order to get really good at CP. So as you scroll down, like a lot of these materials are not very necessary for especially beginners. But with that being said, this is a pretty good like search like site if you want to like self-study something, anything. Okay, that's the first small announcement we have here. Okay, so let's see the. All right. Okay, so this is the first announcement we will have. Okay, so let's have a brief review of what we talked about last class, which was the binary search tree. All right, so can anyone remind me like what is a binary search tree or what kind of property it has? We were talking about binary search tree right at the end of the class. Okay, just make sure. Anyone? What is the property of binary search tree? Okay, I will just get started and work on it. Okay, so a binary search tree, if you can recall, is a data structure in C++, and basically the property is that it's similar to like a list, an ordered list. So you have a root node, which is the one that you always have the access to at first. And then you have like two children on each node. And let's say if you have another node you want to add, basically, let's say this node is say 11, this is 8. So you want to add this node into the binary search tree. What do you do? So this is 6. This is 9. What do you do when you want to add this new node into the binary search tree? Yeah, like what would be the exact like procedure here? Yes.
So you take whatever reference you have, the pointer to the first node, the root, and then you check if it's greater, then you take the right, you recurse. Smaller, then you take the left.
Right, exactly. So the exact computational procedure here is that you take the node you want to insert, you compare it with the root node, and if it is smaller, then you basically go to the left subtree and recursively do the like the previous procedure. And if it is greater, then it goes the right subtree. So eventually, you will reach which is something called leaf, which is basically a node that hasn't been there. So these two nodes actually it doesn't have any children, but it has actually two leaves. So this you can imagine this as a null pointer if you know what is a null pointer is. So basically, this null pointer just they are to be inserted if because they haven't been inserted. So eventually, the 11 will reach one of these null pointers and will be inserted there. So in this case, the 11 will be compared with the root node 8 first, and then it will go right because it's bigger than the 8. Then go right again. So eventually, the 11 will be inserted here. Yeah, that's what happens here, like for the binary search tree that we talked about last class, I believe. Okay, so, all right, so this is a binary search tree, but one important thing to mention is that this is a very easy version of the binary search tree. And the reason for this is because you can imagine something that's like this. Okay, so let's say you have a node, like the root node is 8. And the second node you have is, let's say, 11 or 9, whatever, just to be inserted on the right. And then the next node is 10, 11, 12. Okay, so this is also a binary search tree, right? Just that the case is that every node inserted actually just is always greater than the previous node inserted. So what happens here is that this is like the structure is a binary search tree. But as a matter of fact, this is a pretty bad binary search tree because let's say you want to do like a search operation on this binary search tree. You want to find the element 12, whether it exists in this binary search tree or not. Can anyone tell me what would be the complexity here to find an element, let's say the 12, which is the leaf node? What would be the complexity here in terms of ownership? Yeah, exactly. So the complexity here will be log n because even though this is a binary search tree, it's not, we would say it's unbalanced in the way that you don't have actually any left node, or this is not actually a tree. It's more like a linked list in this case. So that's why this is a pretty bad binary search tree. So, but we have to consider this cases like this always could happen. So the counter solution for this kind of case is something called a red-black tree, or like you can think of it as a more advanced binary tree. So we just call it a red-black tree. So the modification we have here is that instead of just having like the previous binary search tree, like let's recall. So the node, which is just the object we have here, it has only one let's say attribute, which is value, and the child left, which is the pointer, and child right. Okay, so previously each node only has these three properties: the value and left and right. So in this case, if we want to do a red-black tree, we'll just simply add like an extra attribute, which is called color. So what happens here is that each node can only have two colors, like one of the two colors. It's either red or black. So based on that, like this node, the root node always is black. So we have the assumption that the root node is always black. Okay, so based on this, we need to basically do an operation called rotation, to make this binary search tree to be a balanced binary search tree. So that's basically what happens for the like red-black tree. If you're interested in learning red-black tree, there's a lot of materials there, but that's not actually going to be the main focus we have here today. So the important, yes, please.
What exactly is the definition of a balanced binary search tree?
Okay, so that's a good question. Okay, so what is the definition of a balanced binary search tree? All right, so the balanced binary search tree has it has something to do with the height of the binary search tree. So to recall that, what is the height of the binary search tree? Okay, let's say we have a binary search tree like this. Okay, this is the binary search tree, right? Okay, so the height of the binary search tree, as we said previously, is noted as the h. Okay, so let's say what is the height here? So this is 1, 2, 3, 4. Okay, so the height in this case would be 4. Okay, so let's think of what is the balanced binary search tree. Okay, so there's a few cases here. There's a case called the completely balanced binary search tree, in which case is that every node, so basically every node has two children except the leaf node, which in this case here, if I remove this node, this will be a complete binary search tree. completely balanced by the spinner search tree. But this is a little bit too strict, and this is not what always happens. So normally, there's a very specific mathematical definition here. Actually, I'm actually not sure. I'm pretty sure that there is a definition for how do you define the balanced binary search tree, but basically, I'm pretty sure this is not, because if you there's a formula here. Make sure this thing. Okay, so the height in this case would be 5, but okay, I think it has something to do with this. So the number of nodes in this case is n, and the number of height in this case is h. But in this case, height and the h is equal, right? In this case, so this is not a binary search, a balanced binary search tree. So a balanced binary search tree, the height and the number of nodes will be satisfied with a log relationship. So there will be a relationship governed by this instead of linear. But I don't think this is the precise definition. But the rule of thumb is that basically it's not like a linear thing.
Yeah.
Yes.
So Google says the height of the left and right subtree of any node can't differ more than 1.
Oh, the height of the left. Sorry, what's that? The height of
the left and the right subtree can't differ more than 1.
Okay, so all right.
That is definitely balanced.
Okay, sure. Yeah, I'm not actually very sure. I learned this stuff very long time ago, actually. But I'm pretty sure that in reality, there will be very few cases you have a completely balanced binary search tree. Most of the time, you just satisfy with it's fairly balanced. That'll be fine. Yeah, but this is definitely the extreme case we have here. Okay, so but again, we're not gonna cover very deep about binary search tree, especially red-black tree today. Yeah, but if you're interested, there's a class called 382, and I write, I'm not sure, sorry, what's your name?
Steve.
Okay, yeah, so there's a class called 382, and it's covering about a lot of algorithms and data structure, and just the red-black tree is one of the data structures we cover. Yeah, so if you're interested, definitely check out that class. But today we're gonna, the main focus we have is gonna be range query, which is something, pretty interesting. Okay, so here's just what is the definition of a set? I mean, not definition of set, but okay. So the reason we talk about the existing binary search tree is because the underlying implementation for C++ library, the set set data structure, the underlying implementation is using the red-black tree. So yeah, I would say that's probably the only reason you have to know the red-black tree or the binary search tree. So in reality, very few times you will actually write yourself a red-black tree because C++ already provides that for you. So most of the time you just need to call this this set constructor in order to construct a set to store any unique item. So anyone here that doesn't know what a set is? Yeah, set is just it's a set, just a mathematical notation you had before maybe. It stores only unique items within the set. So yeah, that's probably the only reason you would learn binary search trees to understand the set, the implementation of it. Okay, so we have a code example here, just to illustrate how we use binary search, not binary search tree, but set operation. So let's see if I can zoom in this a little. So most of the time you just declare a set using this. This is the type, in this case, an integer. Yeah, and iterator. Does anyone know what an iterator is? Okay, I will explain it. So iterator, if you can recall, what a pointer is. So a pointer basically in C++ is just something that points to the memory location of the variable itself. And the iterator is just another fancy name for pointer, but in the context of a data structure, we prefer to call it an iterator. And in this case, I actually call the method if you can see here, the begin, right? The set.begin. So what this would return me is this will return me a pointer to the beginning of the data structure, which in this case we have here is the set. So okay, set is unordered. Anyone does that make sense? So unlike array or unlike vector, set doesn't have like a specific order in which you can like parse it. So if you have an array, let's say, you have always kind of index it, right? So you start from 0, 1, 2. Array is always ordered. A set doesn't work like that way, because in the set, like the element is not like ordered from 0 to something. So in the set, instead you have an iterator. I mean, technically a vector also has an iterator, but the idea behind iterator is that when you call this function called begin, it returns you basically a pointer to the first element within the set. I mean like the pseudo first element, like not really the first element. Just the first element so that you can actually, each time you update this pointer, it points to the next element within the set. So iterator basically is just a pointer. That's also another reason why it's also very important to learn like the idea of pointer in C++. So okay, I just will walk through this example to illustrate what is iterator here. So as you can see here, it's I call begin, this 8, like it's just a shorthand for iterator. So this variable is just a pointer to the beginning of the set. Okay, so let's say if I have the element, let's say if I call the operator, so if I say I construct a set and I call it S, okay, and I put a few elements into this set, let's say 2, 3, 4, something like this, and I call it begin, right, and I will have an iterator to the beginning of the set. Let's call this iterator it. So if I dereference it, remember like in C++, if you want to dereference a pointer, you always have to put a star sign before the pointer itself. So if I dereference this thing, the value you get would actually be 2. Or like actually this is not ordered because it could like set doesn't have order. But here I'm just trying to illustrate the idea here. Just like this would give you the value of the first element in the set. It's kind of confusing. I think it would be better if I illustrate this like iterator thing with a vector. That would be better, but that's not actually going to be the main idea here. The only takeaway here is just how to use set here. You don't actually have to know like a lot about iterator in this case. So yeah, basically also yeah. So the way this is also a good example like how do you understand iterator in this case. So you see here is also like another iterator and pointing to the beginning of the set. So what is this loop saying is that as long as its iterator does not equal to the end of the set. So this end is actually this function is another function that returns you a pointer. But instead of the begin, which gives you the beginning of the point, like the set, gives you the end position of the set. So that's the only difference here. But end basically also gives you a pointer. Yes.
I thought sets didn't have order.
Sorry, what's that?
I thought sets didn't have an order.
Yeah, set doesn't have an order, but okay, so it doesn't have an order, but so here begin and end only means like okay, in the memory it has the order. If that makes sense. So the memory, if you can recall it, you can imagine memory as a grid. So in the memory, set is actually stored within some order. Like each element is some element in the set. And then at the beginning, basically points you to the beginning of the set, which is like in the memory address, it has an order. And each time you update the set, update the pointer, it points to the different elements within the set. And the end basically means the little mark you can imagine but basically this end tells you that it doesn't have another element. But okay, as I said, this is a pretty bad example, talking about iterator using the set, because the set doesn't actually have an order, but it would be way better if you just imagine it as a vector which has an order. And yeah, that would be better. But maybe we can spend another time talking about what iterator is. But set is just here, it doesn't really make much intuitive sense. Okay, as I said, if you want to dereference the pointer, just put a star sign before it. That basically gives you print out the value of that specific pointer here. Yeah, you can use pointer and iterator interchangeably based on the context you have. Yeah, okay. Yeah, so most of the time you only have to construct a set instead of writing the whole replica tree. Yeah, again, the next thing thing we'll be talking about something called heap. So how many of you heard about heap before? Okay, a few of you, good. What is this? Okay, so anyone want to talk about like what heap is? Like just very generally. Okay, sure.
It's a structure which always outputs the smallest or greatest element contained within it in a very efficient time.
Yeah, that's a very like elaborate explanation basically. So yeah, it is exactly what heap is. So heap basically allows you, like in this case, we're talking about max and minimum heap here. So one of them, for example, you mentioned is the max heap, the other one is min heap. Those are two types of heap. Actually, I asked a pretty bad question, but because I asked you what is a heap, but in this case, we'll only like say examples of it. Because if you can see here, we actually have a ton of different types of heap. Like I know it's a little bit small here, but if you can see closely, I can just read a few examples. So we have like something called Fibonacci heap. So this has nothing to do with max and minimum. It's just the data structure allows you to retrieve Fibonacci number. Like basically, you pre-compute a bunch of Fibonacci number, and you store this into the heap, and you basically retrieve them like using a very efficient way. As to what exactly it is, I'm actually not sure because I only read like a very general list. But the main idea is here is that you have not only mix and maximum, like min and max, but you have like a different variety of heaps you can use. But most of the time, I don't think you have to cover those like topics unless you're interested in. Yeah, they're not just that many frequently. But of course, like as you go along, like you probably encounter some problems that would require you to implement other types of heap. But here, just we talk about like max and min heaps. So yeah, exactly. So in the C++, there are two types of heap. One is called a max, the other one is min. So the difference is that basically max allows you to retrieve the biggest magnitude, like the element with the greatest magnitude each time, very efficiently. And the minimum basically allows you to do the opposite way. And also, just not retrieve. It's not only retrieval, but also like some other operation like update and I say store element into the max heap. So all of those operations can be done very efficiently. And the underlying implementation for this is heap, or you can understand heap as something that's similar to binary, like it is a binary tree, in the sense that you have the same like two nodes. I mean two children for each parent. The same is here, but the difference is that each time like the root node in this case, if you have let's say a max heap, the root node will contain the element with the greatest magnitude. And this is true like recursively. So this root node will contain the greatest magnitude element compared to these two children nodes. So that's the properties of a heap. So and vice versa, like if you have min, this will be the smallest element among all of the nodes. So any question over here like about max and min? Okay. Yes.
Yeah, can you talk about the differences between the array implementation and the tree implementation?
Sorry, what's the array and what?
Like the array implementation.
Oh, the array implementation.
Yeah.
Okay, no problem. Yeah, we'll go over that right now. Okay, so as you can see here, there's actually an array representation of the heap. So okay, let's talk about this part. All right, so as we said previously, the heap normally is a data structure that you can construct using struct, which is just the C++ object. Alright, so the C++ sense of object, which is just a called struct. So in this case, if you want to do like an array, basically what this thing basically is that. Okay. So remember we talked about last time, we talked about something called a family tree or a binary indexed tree. And I said it actually isn't a tree. It is actually an array. So it turns out that a lot of the time when you have like a data structure that's constructed using struct, you can turn it into something that's a one-dimensional array. But you have to use some nice, let's say, number properties in order to make things work. So in this case, okay, so number property we will use is that. So each of these element within the array, it has an index, right? So the number property we will use is that for each of the node, we want to find the children of this node. Basically, there will be 2 children. So one of the children. So how do we calculate the children of this node? So let's say we have the element I. So one of the children would be the location of this children would be I times 2 plus 1. This is one of the children. Let's say it's C1. This is the children index, and the other children would be just I times 2 plus 2. So as we will cover later today, there's a family tree which also uses a beautiful let's say number theory property in order to make this one-dimensional thing work. But here is basically saying that for the element 0, one of the children is going to be 1, the other children is going to be 2. And so for 1 of the children is going to be times 2, going to be 3. And the other children is going to be, let's see which one. Okay, it's going to be 4. And for 2, it's going to be 5. My math is right. Okay, so that's basically how this thing is turned from there. So you can, using this kind of mathematical number properties, you can turn that thing into this thing. And I mean, I can draw this draw a diagram based on this. But the main takeaway here is just that sometimes you can use some very nice properties to construct a very efficient one-dimensional representation here. So this will be 0, index 0, and this will be 2 elements, 1 and 2. And the 1 would have 3 and 4. And 2 would have 5. Yeah, and the 3, the children of 3 would be 7, which is out of the index here. So yeah, the representation would be like this. So you can actually use this number property to convert them.
Is there any difference in the efficiency of retrieval or storage? Or
Yes.
updating?
Yes. So the difference would be that if you use the struct, this you have to define that. Say, so I would say the difference won't be that big as long as far as I'm concerned. Because the reason that in terms of memory, if you have a struct, you only have let's say the let me think what would be the difference here. Okay, so there is actually a difference here. The difference is that if you use let's say a struct, then each time you only have access to the root node, or at least very if you think in the tree way, each time you only have the root node, you have to traverse each of them recursively in order to go to the node that you want to go. But if you have an array, you just can use the index directly to access the node. That'll be one difference, I think. But I think the general rule is that you kind of want to use the array representation whenever possible, because I think this is some math property here that's often turn out to be very useful. I don't think the difference is that big. Okay. Does that answer your question?
Yeah, I think that the difference would be in the update part, right, where you have to restructure them.
Oh, okay. So what would be the difference in this case?
So, for instance, you would take out the first node from the tree, and then you'd have to restructure the tree, right?
That's true, actually.
And the same thing goes for the array, right? You have to move everything.
Exactly. Right? So the update process here would be that if you say you update one element, you have to propagate the change throughout the entire array or entire tree.
Yeah.
But I think these two structures are I would say it's I forgot how to pronounce this word. It's called isomorphically similar to each other. So they are basically there's a bijection corresponding relationship between them. So I don't think the difference is that big, but I'm not actually quite sure about that part. Yeah. So any question over here concerned with the hip? Okay. So cool. So yeah. All right. So this part is the same as before. We have a binary search tree, then we have the set. which is used to implement the set data structure within the C++. So in this case, if we have like a maximum or minimum hit, we can use it to implement something called a priority queue, or just like, okay, so anyone like heard what is the use of priority queue before? Like what is useful? Okay, so priority queue, okay, so it's just another data structure that exactly, I mean the underlying implementation is using it. So you can like guess that maybe it's definitely related to retrieval, like the retrieval of the element with the extreme magnitude, let's say the minimum or the maximum. In this case, if you have the default priority queue provided by C++, each time when you retrieve an element, you would basically have the element with the biggest magnitude. But if you do a little bit change, not very much change, you can just have the reverse effect that you can retrieve the minimum element at each operation of retrieval. There's a code example we can go over, but any question as regard to like what is a priority queue? Yes?
How does it differ from a heap?
How is it different from a heap? Okay. So priority queue is a data structure, and heap is the underlying implementation of the data structure.
Okay.
Yeah. So I would say it's not that different. Like technically, you can call it just a heap, but yeah, I don't think like C++ provides a heap, but it definitely does like with the priority queue. Yeah. Okay. So yeah, let's see an example here, like with the priority queue, which I think is. Also, like the difference between these two might be similar to like when you have a set and a binary search tree. Like their relationship is kind of similar. Like one is the implementation of the other, but some properties are very like shared across them. Okay, no, wait, not this.
I think you meant a linked list, right?
A linked list?
Yeah, right.
Oh,
A stack is implemented by a linked list, right?
oh, that's true. Exactly. That's the same sense applies. Yeah. Okay, so we have a. Oh yeah, this one. Okay, priority demo. So this one is just like a max heap. If you can see like the comments here, like basically the default priority queue provided by C++ allows you to each time just we push in elements, and when we retrieve them, we basically each time get the element with the biggest magnitude. So in this case, if you can see here, okay, so the top, basically this function returns me, what should it return me? Like, here, the maximum element is 30, right? So the first one is to print out 30. And the pop operation basically allows me to delete the element with the maximum magnitude in time. So the next time, when I delete 30, the next time will be 20. So yeah, I think priority queue, like any data structure in C++, has like an iterator corresponding to that data structure. It's basically just a pointer. Yeah, I think priority queue also has one, but I might have to check again. But here I didn't put like a demo. But like any question as regard to this part, like, any question here? Okay, also like how the way to find like the way to let's see okay, the way to implement a minimum heap. As you can see here, we have a maximum heap. So it's actually very simple. So you see here, when we construct the priority queue, we passed an int, right? Okay, actually I didn't put this example. I kind of just to be sure. Yeah, I just one sec. Yeah, it's just a little small change you have to put there. Okay, this is the maximum priority queue. Alright, this is the minimum priority queue. So if you can see here, like, let me zoom in. Okay. So this is the minimum priority queue. Basically, the way you do this is that you pass another parameter here. So you can see here's another parameter. It's not actually a parameter, but I think this is like a generic thing. But okay, we will not go into that part. But here it's just passing greater. The syntax is just passing greater. Basically, it becomes the other way around, which in this case you have a minimum here. instead of a maximum if. So each time you retrieve the element, it will print out a 1, 2, 3 instead of 3 to 1. Does that make sense? So one small change here, like in order to make you like enable you to basically do it the other way. Yeah, okay. So that's the priority queue here. So yeah, the main focus we have today is actually branch query, not the other previous two, because we don't actually go very deep at those two. So okay, let me just read this. Oh, by the way, any question like with regard to the priority queue? Or heap? No? Okay. Alright, the next topic we'll cover is called range query. How many have heard about like the term range query before? Yeah. Okay, a couple of you. Like, do you mind explaining like, or like say a little bit general, like what is actually range query? Anyone?
I think like
Yeah.
we try to pre-calculate the sum of the range in order to like increase time efficiency.
Exactly. Yeah. Like something along those lines. Yeah, exactly. So range query basically something. As you can see here, actually, range query is a very generic term. You want to put something inside, like between the word range and query. Normally, there are 3 types of query we want to carry out. And like the one that we're going to cover today is called sum, so it's going to be range sum query. And there are a couple of different ones, so it's a maximum and minimum. So these two are very similar, so if you know one of them, definitely you know the other. But generally, there will be only like 3 types of query. Range sum query, range maximum query, and range minimum query. So the importance of this part is that a lot of times when you see a problem, you sort of want to like let me see how do I like address this in better context. Okay, so the first thing is that this thing is extremely important. Like one of the few very important topics. I mean, all the topics are very important, but this part is basically like it appears that a lot of problems in CP you have to use this sort of techniques in order to make your solving like problems more efficiently. Okay, but the important thing is that each time when do you want to use this sort of thing? So exactly, you have to pre-compute things. So yeah, actually, I guess we'll go to the example part because that would like make things illustrations easier. Yeah, I mentioned before like this student like Charlie, he's the same sophomore as I am, but he's extremely good at CP. So yeah, actually he and his team went to the American championship like this year of ICPC. So here I'm just using a quote of his actually. So actually it was him who told me that like this topic is very important like in CP, and it's very important to emphasize here that it is actually very important. Yeah, I guess like we'll go into like how do we illustrate this idea, like using one example here. So what is actually a range query? Alright, so we're gonna have like a simple problem in this case in order to demonstrate what is actually a range query. And more specifically, we're gonna introduce 3 different approaches to solve this problem. Actually, 4 different approaches to solve this one problem. But all of them gonna be different, and they all have some pros and cons, like in different scenarios. So all 4 of them are kind of like all 3 of them are kind of different techniques. Yeah, so the last one gonna be family tree, but the first 2 are gonna be interesting. Okay, so the problem we're gonna have here today is that let's say you have like basically n boxes, and each box you have some elements within. I mean some, let's say marbles or whatever, just something within this box. Let's say you have 3 marbles in the first box. this is basically the setting of the problem, which is you have an array or one-dimensional thing. Okay, so you have this one-dimensional vector or array, and the problem is asking that you have two different types of updates or like queries. The first type of update you have is it's just update, which is a function that takes the input of an index and the value of the you want to update. So for example, here we have an array, and let's say update 0, 2. Basically, this would make this first element or 0 element to become 2. That's the update state query we have here. And the second type of like query we have is called sum. In this case, it's because it's a range sum query, we're gonna have the sum. And this is index I, index j. So the second query basically takes two different indexes, and it tries to compute the sum between of all elements between the I and j. So for example, if we say sum 0 to 4, basically this would sum together 2, 3, 2, 5, 8, 10, like sum all these elements together. So in this case, let's say sum 0, 1, this will be just sum these two elements, so it will be 5. So any question regarding to what is actually these two different types of queries? Like any question here? Yeah, so far it's pretty intuitive, I guess. Okay, so the problem is that how would we make these two operations as efficient as possible? So anyone have a like idea like how do we basically like do these two different things? Like how would you address these problems? Like just any idea? Like how do you update things? How do you sum things together? What's your computational procedure for addressing this problem? Any idea? Like any? Yes.
Yeah, so I think for update, it's an array, right? So we can just
It is an array.
The array at that position to
Exactly. And for the sum?
we can calculate like the sum from, for example, A0 to AI as a variable SI.
Yeah.
And then the sum of index from I to j will be like Sj minus Si minus 1.
Yeah, exactly. And okay, that's actually the first method we're going to talk about today. And sorry, what's her name?
Minus quantum.
Okay, very good. Okay, that's actually the first method we're going to cover today. But more specifically, what will be the complexity for update here in this case? All of 1. Yeah, but I mean okay, so you were saying like something that you store the sum of the first few, like let's say you okay, so I'm making sure like if I'm understanding you right. You basically you're saying that you want to compute another array.
Yeah.
Is that right? Okay, so if you want to compute another array, adding within each element of the array, what do you want to put here?
So the first one would be like 0.
Be 0.
Yeah, and then the second one is 3.
Uh-huh.
And the third one is like 5.
Oh, okay, I get what you mean. Okay, basically you sum them together, right?
Yeah.
Okay, so yeah, this will be the first method we have here, but okay, so what would be the sum complexity in this case?
So if we, like in the pre-calculation, it would be O of n.
Yeah, construction phase is open. Yeah.
But after we construct it, it would be O of 1.
Yeah, exactly. But what would be the update phase? Would it still be all of 1 or all of something else? Any idea like what would be the update phase here? Or actually, just let me just go through that part like gradually. This is actually a little bit fast. So basically we basically skip the most stupid, like not the most stupid, but the most simple like solution here. Like it will be just a looping, right? Basically, update will be just all of 1. If we just loop it, like if let's say we want to change the second element, we just change it like from the original array. And if we want to sum the element, we basically just loop, like create a loop from the first element to the end element, and loop and sum all of the elements together. So in that case, the sum complexity will just be olefin, right? Because the worst case is that you have to sum all of the elements together. So in that case, it will be olefin. So this will be the complexity of the most simple solutions we have. I mean, it's not bad. Just one is the olefin, the other one is olefin, and the worst case scenario is olefin. Okay, so the first solution we gotta have, and before going into that, anyone have any other solution like regarding to this problem? Okay, we'll just go into this first solution. Like first the strategy here. Alright, so the first strategy is called a cumulative array. Or I guess without the A, I mean just a cumulative array. So yeah, it's column, right? Yeah. Just to say that actually the solution proposed by Gong is actually just the cumulative array solution. In which case is that, okay, let me just give you a very mathematical definition of what is a cumulative array is. Okay, so suppose that we have this here array, right? This is the original array we have. And let's name this array as B. Okay, so the cumulative array we're going to define is, say it's A. And as a mathematical definition for this A is that the element at index I is equal to sum of the element from 0 to I. And here I is from 0 to N. Okay, so this math is actually a little bit redundant, but it's a little more, makes it a little bit more formal. So what it is saying is that the S element of the accumulative array is equal to the sum of the first the sum of the first i's element in the array B. And where I is from, not N, that's the nice one. Because there are only N elements, so it's from 0 to N minus 1. So intuitively, what it is saying is that, okay, let's construct another array, let's call it A, where the first element of the A is just equal to the first sum of the first elements of the array B, which in this case will be just 3. And the second element would just be the sum of the first two elements. This will be 5, because 3 times 2 is 5. And the sum of the first three elements would just be 10. And 18, 28, 30, 31, 34. Okay, this will be the cumulative array that we built. Right? Any question over here? Or is it like the definition over there? Okay. So, any idea like how this would make things a little bit different from here? Like, so far we have the complexity of olefin update, olefin sum. How would this thing make things a little bit different? Yes?
It would swap the complexities, right? So you would have, you would get the sum between any two indexes immediately.
Yeah.
So O1, right? However, update, you would need to update every index starting from the starting index all the way to the very end.
Yeah. So it would be olefin. Okay, so yeah, that's right. And let's look through why that case. Okay, basically you explained it already, but I guess I'll just a little bit elaborate based on what you said. Basically, okay, so if let's say, let's give it a little bit more like rigorous algorithm, like how would we compute these two different things here? So let's say if we want to find the sum of the element from index I to index j. So what would be the like the mathematical like interpretation, like how do we write this like using like say pseudocode?
How do we write sum?
Yeah, sum I and j. Like what would be the pseudocode here?
For the updated array? Or for the accumulative array or for the original?
I mean the accumulator array. I mean just like say after constructing the accumulator array.
Yeah.
How do you what would be the like the say the pseudocode for the sum operation?
You just have to index into a specific cell and get
Yeah, exactly.
Yeah.
So yeah, exactly. So you just use the let's say the accumulator array at the JDX, which is the next index minus the IDX. Yeah, let me see.
I don't get enough mathematization, but that's okay. I get how it works.
Oh, okay. Sorry, what's that?
No, I just don't understand the mathematical notation.
Oh, sorry. Okay, so this is just a sub index. Basically, this is saying that like the cumulative array A at index JDX, and this is a cumulative array at index IDX. Yeah, I guess like the reason why Kwong said like there's an element 0 is because you want to have a dummy verb, like a dummy value, so that this quantity always holds. But in this case, in this mathematical definition we have here, we actually don't deal with this 0 element. So we have to consider a special case. So the special case is that we consider like what happens if you have a sum 0 to 5? What will be the value you want to return? It would just be a sub 5, right? Like the fixed element of the cumulative array. Because basically that by definition that means that the fixed element of the cumulative array is just the sum of the first 5 elements of the original array. So that's what happens. Like that's basically what you want to have when it's 0 and 5. But when the first index is not 0, let's say it's anything but 0. Let's say if it's 1, then you can just always use this definition, like from a sub JDX minus a sub IDX. Yeah, that's always holds. Yeah, but also it's pretty good like to have a dummy variable here, but that would just make the index a little bit, let's say, yeah, that's also fine actually. I mean, in this case, if you have a dummy variable here, let's say if you want to find the element, some element from 0's element to the i's element, then you just always can use the a sub I minus a sub 0, right? Because 0's element is 0. So it's also like makes sense if you just use the dummy variable like at the beginning. Yeah, so it makes sense so far. Like, yeah, for the update operation, let's say the worst case is gonna be that. Let's say if you want to update the first element, right? You want to update to, let's say 2. Then you actually have to change the entire the cumulative array, right? You have to build it from scratch because all of these elements have dependency on the 0th element. So yeah, that's why you have to basically reverse this two different operation complexity. Okay, so far good. Like any question here? Okay, so that's it for the cumulative array. So actually, a few days ago, I had this interview question. It was based on some idea that's similar to cumulative array. But instead of a cumulative array, okay, let me actually read this one first. Okay, so this is not an example that actually, if you learn this thing, you want to sort of expand this idea to other areas. So okay, let's say you have a matrix. We sort of want to apply this idea of thinking to something a little bit more high dimensional. Which let's say we have a matrix of size, let's say m times n, m rows and columns, and say you have this matrix. Okay, so the idea that it's exactly the same. You want to have two different types of curves here. One is update, the other one is sum. Like how would you build okay, so the sum, let's say you have the coordinates of two different grid. Let's say you have this grid and this grid. Sorry, these two grid. I mean any grid, like any two possible grid. So these two, let's say. So you want to find the sum of this grid. Does that make sense? So you want to find the sum of this area. Let's say this area. Okay, so how would you use the cumulative array to apply to this idea here in order to make operation faster? More specifically, make the sum operation faster. How would you do that?
So
yes.
I think you call the bottom 0 as the ij.
Which one? Sorry.
Like the square, like the bottom 0 as
this
ij.
one?
Yeah.
This one?
Yeah, yeah.
Oh yeah.
You call it like ij.
IJ. Using what the index is ij?
Yeah, I mean like the coordinates of it.
Oh yeah, exactly. Okay, no problem.
Yeah, so I think we can create like a sum like similar to the array, but like now we will consider the first point would be the upper left corner.
Oh yeah, this one.
Yeah.
Okay. So start from here. Okay.
Yeah, and now sum of ij will be the whole
This area.
yeah, this area.
Okay.
So basically sum of ij will be equal to like sum of I minus 1, j minus 1.
Yeah, you mean like sum of ij. You mean like this grade would just be this like the whole
Yeah,
sum
the whole sum.
minus this part,
Yeah, that's right.
and what else?
So it would be like sum of I minus 1j plus sum of I j minus 1
Yeah.
minus sum of I minus 1j minus 1.
Okay, I'm just gonna like say what you said, but yeah, that's exactly right. So the idea here, you want to apply the same like idea here, and the way you do it is that basically the mathematical definition would be that like let's say you have a let's say you want to compute the cumulative matrix, and you want to compute like the value of this part of this point, right? What you do is that you basically sum all of the elements from the left like from the left diagonal all the way to that diagonal, like the point where you want to end. So in this case, let's say if this is 1, right? Like this is the original array, let's say. All of them is 1, right? Okay, so this element in the cumulative matrix would just be 9. Because the sum of all of this 9 coordinates is 9. I'm not sure if that makes sense, but like the let's see, okay, so let's think of how to explain this. Okay, so what you want to do is that you want to start with the left diagonal, go all the way to like say any of these points, and compute like this whole rectangle. I don't want to sum all of the elements within these rectangles. That's how you compute the cumulative matrix in this case. Does that make sense? Or
So it would be 1 and then right underneath it 2, underneath it.
yeah, let me make this not so 1, maybe it's a little bit simpler. 1, 2, 3, 4, and this 5. Let's give this an example. So this is 1, 2, 3, 4, 5, and this is 2, 1. Let's work with this smaller like case, like how to construct it. So this would be 1, right? And this would be
3.
yeah, exactly. So this will be 6. You basically sum this together. This is the sum we always do. And this will be like just a sum all of them together. Right? This one. Right? And this one will just be sum like these 4. And this one will just be sum of this 6. Okay, that's how you do the accumulated matrix. And the way you compute like arbitrarily two points. Let's say if you want to compute like the sum within this small rectangle, right? How would you do that? Like you start with this point, right? This point would give you the sum of a bigger rectangle, right? I mean you want to find like this rectangle, which is a small one. But you start with this one because this will give you like a bigger rectangle, and you want to sort of subtract these small rectangles. Right? Does it make sense? Okay, so the way you do that is you start with this rectangle, and you have this 16 different sums, and you subtract the let's say this part you don't want, right? This is the border part. So the way you do that is you basically subtract this point, which gives you like these 4 sums, and subtract this point, which gives you this 4 different points. And you subtract them both, then what else do you need to do?
Plus the square at the upper.
Yeah, exactly. You have to pass this back. Because when you subtract this and subtract this, you basically subtract this one twice. You have to add one back. Yeah, that's how you solve this one, like a cumulative matrix using only one operation. So it's pretty fast. So you do some pre-computation which takes all of the square, but offline each time for doing the query. Yeah. So this is the problem I had a few days before, but it's using exactly the same idea behind cumulative matrix. Yes, please.
I understand how you can subtract the top one, right? Because it's just like the value on the very right. How do you subtract the one that's vertical?
Okay, so I guess I'm not saying like very clearly definition here. So the definition of the way you calculate this element is that so geometrically you always start with the most left one, and you draw a diagonal. So the area that you crossed in this diagonal line is also the sum of the elements. We need to sum all of the elements. So in this case, like this one, right? So when you're pre-computing the values of this element, you basically sum together like all four of these elements. This will be like you sum all four of the elements. This will be the value. That will be the value of this element. Does that make sense? Or
I thought we were summing horizontally.
I mean, okay. So consider like what would be the element of this element? What would be the value of this element?
It would be all the values on the top row and one on the left.
Oh, actually no. I didn't explain it right. So the value of this element would just be starting from the most left to most diagonal to this diagonal, and then cross the line. So it will cross all of these four elements.
Okay, understood.
Yeah. So in this case, it would be 1, 2, 1, 1. So this one would actually be 5.
Got it.
Instead of just but it's also actually possible. You can think of this matrix as one giant one-dimensional matrix. So you go like from left all the way like this, right?
Yeah, that's
So that would be one-dimensional. But in this case, I don't think like that would be also fine. But yeah, I guess we can just use this. Yeah, it's just but the idea is always kind of similar. You just use like accumulating sum all the time.
Okay.
That makes sense. Okay, got it. Alright, but like going a little bit beyond, but you can also go a little bit more hyperdimensional. This is 2-dimensional. You can do like n-dimensional, which is something called tensor. I actually have no idea what tensor is, but it's some high-dimensional object that you deal with in tensor, like something called PyTorch, I think. Yeah, you have a tensor and you can apply the same idea there using the same pre-computation, and you have to make things faster. So what would be the good scenario for using this kind of data structure? What do you think? Like, in terms of if we have this operation things, what would be the good scenario here? When do we want to use this kind of data structure?
When you want very good summations, I guess.
Yeah, exactly. So that's true. So when we want to have like very quick summations, but also we have very few time-flow updates. Yeah, you want to make sure that there's as few updates as possible because each time we do updates, it's actually very slow. Yeah, so that would be the good thing here. So each time you make sure that there will actually be very few updates. Let's say you have a database, and there will be a few updates, but you often do this kind of something. So you want to do some pre-computation, like with the data you have, in order to make things faster later. Yeah, that would be the scenario here. Okay, so let's see how much time we have. Okay, turns out that we went slower than I expected. Okay, I guess I'll start with this one, but I will go with this one a little bit first. So the second strategy we have is called square root decomposition. Yeah, how many of you heard this term before? Oh yeah, do you want to explain it a little bit or?
So just we may maintain some data structure of the depth is the root of n, and we maintain this data structure. So every time we want to calculate something, we use this data structure to know some range about the root of n, and we go inside and we
Yeah, that's basically it. That's basically what is happening here. So the scenario is the same, that you have let's say a big data structure, let's say this giant list. So what you do here is that basically use some divide and conquer strategy here. So what you do is that you have this list and the size of it is n, right? So you divide this list into sublists, and the size of each sublist is the square root n, and you make it upper bound. If you don't know what upper bound is, basically if you have let's say a fraction number, let's say 1.02, this is the fraction number, and if you make it upper bound, this gives you 2. This is what upper bound is. Okay, so basically it returns an integer if you have a float, but also always it runs upward. So let's say you have this array with size n, you square root n, and you make the upper bound of it. This will be the size of the small segment of each sublist. So what I mean is that here is that, okay, let's say you have a Okay, let's make 9 here, actually. So let's make it one more element, which is 4. Okay, just to make things a little bit easier to illustrate. So here we have 9 elements within this array, right? So the size of each sublist would just be square root of 9 and make that long. So this would just give you 3, right? I think it's 3, right? Should it be 4 or? Wait, I think it should be 3. Okay, whatever. But I mean, the case here is that you have each of the sublists of the size 3. So this would break this giant list into 3 sublists. So the first one is going to be like these 3 elements. And you basically do the computation for each of the sublists. So the first one will have like a sum of 10, right? Second one would just be 20. And third one would just be, let's say it's 8. Okay, so if you want to update an element, basically, let's say you want to update this element, the third element. So let's say you want to change it from 8 to 7. What you do is that you just update the corresponding value of the pre-computation value, of your pre-computed value. In this case, it's 20. So, like you minus 1, basically just minus 1 to the 20 gives you 19. That's how you update things. And same sense is here, like say you want to update the 6 element, you want to make it a 2, from 1 to 2. Just add 1 to the 8, this will be 9. Okay, so what would be the update complexity here? It would just be all of 1, right? Because like say you want to find an element, just first find which component this element belongs to. Let's say if it is 3, then like you basically count like which component it is. If it is second component, you just update the second, like the value of the second component. So the update complexity would just be all of 1. And the important question is, what is the sum complexity in this case? Any idea? Any guess?
Square root.
Yeah, it actually would be square root n. And the mathematical justification for this is a little bit complex. But the way you do sum operation with this divided list is that, let's say you have let's say the gap between n and j is pretty big. Like say if there's 1,000 elements within, like between n and j, then assumably there will be a few like the sub-blocks within those elements, right? So you basically just add the sub-blocks instead of adding up the individual previous elements. So that will save you some time. But what happens if you break this to like, if you want to, like, let's say in this case, if you want to find the sum between I is from 1 to j from 7 to 7. So how will you do this? Basically, you break this, like this one component into like half. You want to sum from 1 instead of 0. What do you do here? You just basically just sum like individual elements instead of so actually just pretty simple. So just sum the individual elements. So in this case, you want to do from 1 to 7. You just sum 1, 2, and then 1, 3. That's it. And the components for this component, just take the 19. So whenever you break the component into halves, you basically sum that part like individually. But if you didn't break it, you just take the pre-computed value. Okay, but also like even if you break like a little component, like even if you break it, the number of elements you sum wouldn't be more than square root n, right? Because that's the size we pre-computed. So even if you break like a small component, the size of it, like the number of elements you sum, wouldn't be more than square root n. So that's why it guarantees that the number of operations you do always is less than square root n. So yeah, there could be like a more rigorous mathematical like definition, but I don't think there's a lot of points that are going deep in there. But the good thing here is that this idea cannot only be applied to something like a range query, but also like it can do like range sum query, range minimum query, range any kind of query. Because you imagine like if you have a, let's say, minimum query, you basically still pre-compute the minimum among this small component and you update from there. So you can do any kind of these operations within all of square root n. Let's say you have a big database. You can also break this database into sub-like databases, and you basically do some pre-computation for each of the sub-database. And instead of updating the whole database, you just updated the small individual database instead. That would be like make things a little faster. So divide and conquer here is pretty important. And why would this be a lot better than the linear solution? So the reason is that if you take a derivative of the linear solution, you find that the derivative of n is just 1, right? So as n grows, grows to the infinity, the function grows linearly because the derivative is 1. But if you take the derivative of the square root n, so it turns out that the derivative of this would be, let's see what it would be. Yeah, square root. Okay, so I think it will be 1 over 2 times square root n. So as n goes to the infinity, what would this value be?
0.
Yeah, exactly. So as n goes to infinity, because n appears to be the lower half of the fraction, so this would approximately be 0. So as n goes to infinity, the complexity will actually not grow. In comparison to this case, it actually grows linearly with the size of the input. So this would be the good case. So this would definitely be better than this case. So the general rule of thumb is that in computer science, very few do you actually use if you have a big list, you always want to pre-compute it. Do some pre-computation based on it. Because that will always make things a lot faster than otherwise it would be. Square root is way better. Okay, so we actually don't have time to cover the boundary tree here, which is the complexity would just be log n for each of the operation here. But the important thing here is that boundary tree generally uses some nice property of numbers. Basically, when you turn into a number into binary forms, there's some mathematical properties that allows you to extract do some operation find the children and find the parents of it. See how much time do we have? Oh, okay, it's already off time. So I guess we'll cover family tree next time, and possibly some of the segment tree, because the segment tree is definitely way more harder, I think, than the family tree. Because the segment tree also allows you to do maximum and minimum operations instead of just the sum queries of the family tree. Yeah, and also there are quite a few examples in this part of the code. Yeah, so we'll do that next week. Okay, so have a good weekend. Thank you very much.